Okay, so I want to spend a little more time looking at residuals. We just sort of touched on it and we hit it a little bit harder. We talked about residuals before. Residuals are the observed value of your y minus your predicted value of your y. So kind of need to understand what that means. This is of the y value. I should have put that in there. So our observed value is our data here. Okay, so if we're looking at this, remember we're years, we start at 0, and then this is year 1, and so on. So this is our x-axis, and this is our y. So we're talking about years and the attendance to the spring concert. So if I want to know what the residuals are, and remember residuals tell us how closely this is to be a linear function. So residuals help us identify if our two variables are linear, okay? And that's where our R value comes in too. When you have an R of 0, that means there's no correlation, or they're just not linear. They may be quadratic or exponential or something else. So we have to look at how we calculate this R value, and we calculate it by taking the observed Y value minus the predicted Y value. So observed is your actual data. So if I wanted to look at this, I might look at 805 is my observed value of the y. Now if I want to find the predicted value of the y, I need the linear equation. So you want to bring your calculator up. You might want to pause the video and put in this data as I have here so you're ready to go. So you can do it with me. So to get the predicted value, we need to get the linear regression line. So that would give us this right here. So I want to put that in my y equals so that I can use the table feature we talked about the other day. So to put that in the y equals, we're going to go stat calc 4. But here I want to put in the, go to the vars, the variable sign, and I want to go y over to y variable. I want it to copy the function into my line 1 and hit enter. Remember, those of you guys that have the other calculators, you put it under store regression equation in your linear part, and then you hit calculate. So now that I've done that, I've stored it in here. And now I don't have to round, because when we round, you're cutting off part of the value and you're actually changing it. You're just getting an estimate. I want to get the actual. So now that I have this in here, I can use my table function, okay? Now the table function is above the graph in blue, and that's going to tell me what my coordinates are for this line right here. So I can do second table, and it shows me now this is my predicted line. So at 0, it's saying it predicts 771.24, which our actual is 789. When x is 1, it predicts a y value of 796.41. So 796.41 is the predicted value. The actual value was 805. So if I subtract that, that's going to give me the residual. Okay, so let's see what happens when we get that. And if you missed that, pause the video and go back. Okay, so I'm going to second quit to bring me back to my screen, and I'm going to do 805 minus 796.41 equals 8.59. So we have a residual and our difference in observed value, and y value is 8.59. Okay. If I wanted to look at this one, when x is 2, our observed value is 773, and we're going to subtract that from the predicted value, and again I would get the predicted value from the table of the line. So that's when y is 2, so my predicted value is 821 point something. What was it? 821.58. Okay. So again, I want to take my observed value of 773 and subtract it from my predicted value, and then this would give me 773 minus 821.58. and we get a negative 48.58. Okay. Now what we want when we do these residuals, we want them to not have a pattern. Okay, if they don't have a pattern, which means they're not the same amount every time, it's a linear equation. Okay, so let's go back to here, and I talked to you the last video on how to do your residuals. If you remember, we went second stat plot, we turned that on here, and then we wanted the X list of line 1, but we wanted the Y list to be the residual. And remember, we got that by doing second list, and then 7 was residual, and we hit enter. Okay, so now I have the X list, and it's going to do my residuals, and my residuals are the observed value minus the predicted value. So it went through and subtracted the actual Y amount from the predicted Y amount. Okay, and so then we're going to go zoom. I think we did zoom fit, did we not? Or zoom stat. I think it was zoom stat. All right, and then you can see here that here are my points. There's one here, here, way down here, up here, up here, up here. This is good. You have a linear regression equation if you have no pattern here, and the observed versus minus the predicted are all over the place. So if we look at a couple examples here, this is the residual plot, right? This is kind of what we just looked at. This is an example of the tree age years and the residuals. And if you look, these residuals are all up and down and in no pattern. So that means the tree age years are a linear equation. So there should be no patterns to the residuals, okay? It's a good residual plot if they're randomly scattered everywhere. So if you look at that example, that works. If we look at this one, the batting average example. So this one again, here's the residual line, and again, they're all over and no pattern. So the batting average is a linear equation, okay? So then we're going to look at orange juice, okay? And it's talking about the pectin in the orange juice. Now you can see they're all clumped here and all clumped here. So this is not a very good linear equation, because they're kind of all grouped, they're not spread out and random. So I would say that the orange juice example is not a linear equation. And again, if we go down to this one too, this one's about the old faithful geyser and the interval among eruptions. So again, these are not random and spread out. So again, the time the old faithful is going out is questionable whether it really is a linear equation. And then if you go down here, this is obviously a not because it has a pattern. Anytime you have a pattern, that means it's not a linear equation, it's a different function. It could be quadratic, it could be exponential, and so forth. So we know that our line has a good residual plot if it looks something like this, okay? Here's another example, random pattern, which means this is a good linear equation. This has a pattern, and this has a pattern. So whatever we're graphing here is not linear, okay? And here's another one. This is temperature in Celsius. Again, these are all over the place. They're spread out, and they're random. So the temperature that they graphed here would be an example of a linear line, okay? It's a good example. So hopefully that helps a little bit. So what I want you to do is in class today we finished 2, 4, 5, and 6, where we came up with these problems. It was a worksheet that I handed you. What I want you to do is I want you to, for each one, put it in your calculator, come up with the residual, and then using the residual plot, I want you to write on this paper, you're going to put residual, and then you're going to tell me whether there was a pattern or random spread, okay? And I hope my head's not in the way here. Let's move this. So, oh, that wasn't really what I wanted. Sorry. I want this. There we go. Let's move this over here. So I want you somewhere on your paper to write residual plot. Tell me if you had a pattern or they were random numbers. And then if it's random numbers or a random spread, that means it is a linear equation. Okay, so for 4 of them, I want you to find the residual plot, and you will bring this in on Thursday, because I'm not going to see you tomorrow. So go through on this worksheet. You'll have 3 to do now. I want you to see if you can calculate the residual plots on those, and we'll talk about it on Thursday. Have a great night. I hope my 8th graders have a good field trip tomorrow, and my 7th graders have a good time with their grade level. We'll see you Thursday.